All right, now let me show you how Euler's method works. And it's just a matter of introducing a little bit of notation. So what we'll do today, we'll apply Euler's method with 8 steps instead of 2 to approximate the solutions of the ODE y prime equals 3 plus t minus y on the interval 0, 4. And the idea is, first of all, we want to deal with the t values. So we have this interval 0, 4. And n equals 8 means we'll divide it up into 8 pieces. 1, 2, 3, 4, 6, 7. So 8 pieces. And the first thing we need to find is what's called the step size, which is just the width of each piece. So step 1, find the step size h. Step size h. And well, either you can do it intuitively or I'll give you a formula. So what we have the interval 0, 4. We want to divide it up into 8 pieces. So each piece has size 1/2. Okay, so 4 minus 0 over 8, which is 1/2, like 0.5. Again, which makes sense on this picture. And again, if you want to do it in general, h is just whatever your interval is. Let's say if it's a comma b, it's b minus a over n, if you want. Now, once we have the step size, so the length of each piece, what this gives us is a bunch of t values. We have t0, which is 0, then we have t1, 1/2, t2, etc., up to t8. So again, what you can see is just simply 0, 0.5, 1, up to 4. So that's the analog of before we had 0, 1, and 2. Now we have 0, 1/2, 1, 1.5, up to 4. That gives you the t values. So step 2, or just gives us our t values. Again, which you can just do using intuition, or I'll give you a formula again. T0 is 0, T1 is 0.5, T2 is 1, up to T8, which is 4, or in general. If you want Tn, you start with the initial point, A, and you add how many times your step size, so a plus nh. Because it's really, you start at 0, you add h to get 0.5, you add h to get 1, and then 1.5, up to 4. Now, that is for the t values. And now the idea is, well, we want to find the y values. So step 2. Find the y values. So the analog of what we did before, y of 0, y of 1, y of 2. So except here we want to write it in terms of subscripts to say like each iteration. So y0, let's say y of t0, y1, which is again roughly y of t1, up to yn, or y8, which is y of t8. Now, y0 is the initial condition. And again, if you want in terms of a picture. So y0, this might be y0, this might be y1, y2, etc., up to y8. Okay. Now, y0 is the initial condition, because that's what we have. E0, which in this case, y0, which is 1. Condition. And then for the other values, we want to use, once again, future equals present plus ODE. So the formula for Euler's method is as follows. Method, lo and behold, again, remember future equals present plus ODE, or in other words, the next term, yn plus 1, equals to the current term plus the ODE. So think hy prime, or in this case, h f of yn tn. And again, if you want to see some motivation behind this, I highly recommend you watch the previous video on this. And again, what is f? It's literally the ODE. So here, f is given by the ODE. ODE, namely, in this case, y prime is f of y comma t, which is simply 3 plus t minus 1. So I will show this in a second, but let's just calculate a couple of values, see what this gives us. And then the cool thing is at the end, we can plot everything. So I'll show you some really cool plots. So y0, we already said, was the initial condition. y1 was y0 plus h of f of y0 t0. Again, present plus ODE, which in this case, it's 1 plus 0.5 f of 1 comma 0. So it's similar to before. This is 1 plus 0.5. Again, 3 plus t minus y. So 3 plus 0 minus 1. 3 plus t minus y. And we can calculate that. And we get 1 plus 0.5 times 2. And that is just 2. So that is roughly our value at 0.5. Well, we can continue. y2 becomes then y1 plus h of f of y1 t1. So now we can use our new value y1 to calculate y2. So it's 2 plus 0.5 f of 2, 0.5. That gives you 2 plus 0.5. Again, 3 plus 0.5 minus 2. And that is 2 plus 0.5 times 1.5. And you can calculate that to be 2.75. And you see, then you can simply continue and continue to get successive values. So y3 would be y2 plus h of f of y2 t2, and then you would get 3.375. And then for the other values, if you wish, then you get y4 is roughly 3.94, y5 is roughly 4.47, y6 is 4.98, y7 is roughly 5.98, 5.49, and then y8 is 5.99. All right, and you may wonder, what's the point of this? The point is literally points, because then what we can do, we can then plot So why important? We can then plot the TI, what all the time and function values on a chart, on a graph. And in fact, I want to show you what this looks like. It's very nice. Let's see if I can find this. Let me copy paste this. Copy, hopefully that works. It does, you see? Because then what you can do, so we had those values, 0, 0.5, 1 up to 4, and then the corresponding y values. So for instance, that would be, so T0, that would be T2, that would be Y2, and then that would be T2, Y2. So to get a plot of points, and then what you can do then is connect the dots, just like Steve Jobs said, and that's the point of the next picture. You can connect all the points here. And you may say, well, is that close to the true solution? Well, that will be more the point of the next lecture. But the cool thing is, in this example, the ODE was not too bad. In fact, it is solvable. So let me remind you what the ODE was. It was y prime equals 3 plus t minus y with y of 0 equals 1. So you can actually solve this if you want using integrating factors. So I think y would be t plus 2 minus e to the minus t. So integrating factors. And then what you can do, and that's really cool, you can actually compare it to the true solution. And this is what you get here. Let me copy that. And you see, in fact, the plot that we had before, the blue line plot, is actually close to the true solution. Because again, this was, let's see, this was the stuff that we found from Euler, the blue line. And the red plot is the true solution. In fact, now you can see this is, at least in this example, it is true. And in fact, you'll see also the smaller the h, the better the approximation. But this will be sort of the point of the next lecture. The last thing I want to show, though, is why that formula is true. So why do we have yn plus 1 equals yn plus f of, or h f of yn tn? Again, that's just using the definitions and the ODE, because yn plus 1 is y at the future value, but tn plus 1, so if you want, this is tn plus 1, this is tn. What separates them is just a step size. So tn plus h, and then again, by our linear approximation, it's roughly y of tn plus h y prime of tn. That was from the previous video, and that is, by definition, yn plus h, and then our ODE, which is f of yn tn. So in fact, this is true. And again, on the menu is another example of Euler's method. And then in the next lecture, we will see why Euler is awesome and why it is terrible. Terrible.